about those slides today. So just as a heads up. All right, today we're going to talk about calculating pressure forces on plane surfaces. And we're going to start that on flat horizontal planes. But then as we start to think about vertical planes or planes that are at an angle, we just have to be very careful about how we do it because we'll go into detail about this, but the line of action of the force is not necessarily the same place as sort of the centroid where we would expect it. And yet we know that pressure increases with depth linearly. So we just have to get into the right mode to think carefully about what we're averaging where to try to figure out the total force magnitude, because that's going to be due to the pressure distribution on a wall or on a surface. But its location of action will be a little bit different. So we'll talk about the gory details today. I don't think I have any announcements. I have not yet brought over all of the participation grades into the gradebook. So those are still missing, but I'll pull those in since I reset the class last week. And then I'll also pull in this week's participation as well after class today. There's this big football game coming up on Sunday afternoon, so no idea, whichever side you're on. Hope you enjoy it. I think there are maybe a lot of people who maybe aren't interested anymore when it became these two teams, but who knows? We'll see. Homework 4 should be posted as we start class here. I think I released it at 12:45, so those should be available to you, those 3 files. And again, remember to look under the assignments tab, and there are 3 pieces. So there's the Wiley part, which will be 8 questions, and that part will be part 1, written. To some extent, we've also talked about the forces that result from pressure. And the simplest version of this is, of course, to think about horizontal surfaces that are at the bottom, underneath. You're going to be on campus for any reason, and you need accommodations on campus or not. So with that, I'll be happy to launch in unless there are any burning questions. Okay, terrific. Okay. Up till now, we've talked about pressure, and to some extent, we've also talked about the forces that result from pressure. And the simplest version of this is, of course, to think about horizontal surfaces that are at the bottom, underneath some amount of fluid that is built up. So if we look at this tank here on the left-hand side, this figure, we have some specific weight of some fluid being held at a depth h. And if we wanted to know what the resultant force, F sub r, was that was acting on that horizontal plane that is the bottom of this tank, we would take the area of it and we would multiply it by the pressure that's acting at that depth, right? So we could write, let me see if I, no. I just want to move you. Okay. Maybe he'll be out of the way down there. All right, so let's see. Oops, let me go back. Oh, I put the subtitles on? Yeah, sorry. Okay, let's do it this way. I just need a pen. Okay, so we said that the resultant force F sub r would be equal to P, the pressure at the bottom. And because it's a horizontal surface, remember we've been saying that the pressure at a single elevation is the same, right, in our fluid column here. So it would be P times A, where A is the area that we can't see, right? This could be circular, it could be square, it could be rectangular, it could be in the shape of a buffalo if it was a pool of constant depth on the CU campus, etc., right? We don't necessarily care about the shape. The point is, as long as there's a horizontal plane surface, the F sub r will be equal to the pressure at that depth, at that elevation, times A. And we can rewrite this then to say that this would be gamma times H times A, right? That our pressure is equal to gamma times H. Okay. So it's also not difficult to know that, or to think about in this horizontal surface context, that F sub r, a resultant force, acts in the middle of the bottom surface. Okay. So this is fairly straightforward. It becomes essentially more complicated. It's supposed to be an L. Complicated. For either vertical. Sorry, I'll try to keep my, I think my writing is clearer when I use all caps. Okay? And we'll talk about why that is. Largely, as you will expect, it has something to do with gravity. Okay? All right. Let's move forward to the next slide here. I'll do that over here so I don't goof this up. Okay. So on the left-hand side, we see what we saw on the previous slide. Pressure on a tank bottom, fairly straightforward. On the right-hand side, what we see is that when we can compare the vertical surfaces, now we have a slightly different perspective, because on the horizontal surface, on the left-hand side, the pressure was the same at every square centimeter of that that horizontal surface for the bottom of the tank. When we're looking at the vertical surface, we have to account for the fact that pressure is changing as we go deeper and deeper, right? So the pressure at this point, at this elevation, is smaller than the pressure at this elevation, right? Now, the math is not going to be that hard simply because this is a linear increase, right? To figure out, what the average pressure is and multiply it by this area is not actually all that difficult. So the challenge we run into is that pressure is not, that was supposed to be an S. Boy, that did not come out. Is not evenly distributed. And so the questions we have to ask then are, how do we calculate FR, right? And that will be fairly straightforward. The real trick here is figuring out, where does it act? Okay, and the hint I will give you ahead of time is that it may not act where you expect, which is to say, it rarely will occur in the center of the shape that we're looking at. So the center of this side, it's actually going to be skewed. And that makes sense because you've got this distribution of pressure with depth, right? We'll take advantage of that for calculating F sub r, and then when we we'll figure out how to deal with that when it comes to looking at the the line of action as well. Okay, so let's go back to some topics a number of you may have hoped that you had completely moved on from, and I don't blame you. I remember going through statics and dynamics and having to figure out centroids and moments and so forth, and that was a bit challenging. We're going to go back through it again right here because it becomes really important for figuring out those two things. What is FR, figuring out what that resultant force is, and secondly, figuring out the location or or depth of the line of action for FR. All right. Okay, so the centroid of a shape, we could have this. This is kind of a roundish shape, right? It's not some kind of regular shape. It's not a triangle, a rectangle. It's not even quite a circle. And regardless of the shape, we can write an equation that says that the centroid of this shape we can break it up into a whole bunch of little DAs, little representative areas that make up the entire shape itself. And we're going to think about this really in 2 dimensions here. All right. So there is some width to it, but remember that the pressure doesn't matter in the X or, well, the horizontal direction. I've used Y as the vertical here, so I apologize. I'm not trying to confuse you, but in the past we've called that Z. In here, this case, Y is now vertical. All right, as we're working in sort of XY space. So X is horizontal. We don't have any variation in the X. So when we take centroids, when we take moments, we are going to take those about the X-axis. All right. Okay. So here we have Y, which is a height that is related to this particular little dA, right? Some pixel, let's say, of some representative small area of the total shape that we have. The total shape has an area A, right? The entire. We are going to look at dA as a little discrete portion or piece of A. And then we also have this Y sub C, which is the elevation in this case, compared to Y0 of the centroid, okay? So Y sub C, when we use C in this context for the rest of today and over the next week or so, that C is going to indicate centroid. The Y in this case is a general height related to dA. So in this case, for those of you who are pretty savvy with this, you'll remember that we are going to integrate over A times of Y dA. It's defined as Y sub C times A for this centroid of a shape, and we can solve then to say that the elevation of the centroid is equal to 1 over A times the integral over the total area of Y dA. Okay? Now, this is going to come back to be a couple of these, as I introduce them, are going to come back to be useful to us a little further down the line in a few slides. So I may jump back and forth just a little bit to point some of these out. But there's our centroid location, or an equation for figuring out in this case, the elevation. And that's really the kicker. The elevation is really the key here because we have the change in pressure in the Y, in this case, the Y direction, the vertical direction. Okay, moment of inertia about the centroid. Okay, so now, if we forget about the fact that, we have this this datum that we talked about before, right, on the previous slide. If we want the moment of inertia about the centroid, we're going to have to consider how area is distributed on above and below the centroid. So now the Y that we care about is reference to the elevation of the centroid, all right? I'm supposed to write something in here. Okay, so the moment of inertia about the x-axis and the centroid is equal to the integral over area of y squared dA. Okay. Now, when we get into specific shapes, and I'm building up to this, in a couple of slides, you'll see some very specific shapes with equations for those particular shapes for these moments of inertia and so forth. You'll have very specific equations for those. So the hard part is sort of done for you, but you will have to know which one of these to pull into the problem that you're working on. Okay, so moment of inertia about the centroid is an equation that looks like this. And then, oops, not sure why that's not advancing. Back here. And then the moment of inertia about a datum, so now going back to having this y equals 0 now, y is referencing the height of dA over some elevation of interest here. We now look at this and we can write that this moment of inertia, Ix, is equal to the integral over the entire area of y squared dA, okay? So those two look the same, but what I'm building up to is this next one. And in the next one, we want to evaluate the parallel axis theorem. All right, so the parallel axis theorem now has us thinking about what is y sub c. So what is the elevation relative to a datum of our centroid? And then how is area distributed above and below that centroid? And again, I'm being specific about above and below because we're working in the vertical framework here, all right? So in this case, we would write that this moment of inertia is Ix is equal to the integral over the area, it's supposed to be an area, A, of y sub c, so the elevation of the centroid plus y, and remember now y is being measured from the elevation of the centroid, so that's the datum, the sort of local datum for y. We square that sum and we evaluate over dA. Now, I'm going to write a longer equation here to work this out. So this is a polynomial, right? So I can take y sub c plus y, multiply it by y sub c plus y, and expand it out. So I'm going to do that, and from that, we're going to make a simplification to make this a little more palatable. And yeah, okay, I do have that. All right. So Ix here now is, you know what, I can do it over here. Sorry, I'm going to keep, I don't want to run out of vertical room, so I'm going to work over here, but I think I can fit it in. Okay, Ix is equal to the integral over A of y sub c squared plus 2 y sub c times y plus y squared dA. And we could take that a step further and pull out a y squared from, or separate these variables. So we would end up with y squared times the integral over a dA, right? That's this piece right here. And then we would add that to 2yc multiplied by the integral over a of y dA, and then we would add the integral over the area of y squared dA. Okay.
Should one of those be a C?
Yeah, one of those should be a C. I think it's the first one, actually. Yeah, thank you. I was just realizing two of those look too similar to each other, so thank you. Yep, so that first one should be a y sub c, and I'm just going to note it on my notes so I don't forget. Future. Okay. And then we're going to do some simplification here. This integral of dA with respect to the area is just A. Okay, so that term becomes the area. So the area times y sub c squared. And then it turns out that this term goes to 0 simply because we have a multiple of the y coordinate of the center of mass, which ends up being 0 in this case. And then we end up with this being equivalent to I sub xc, which I believe we wrote a couple of slides ago. So this boils down to now Ix, our moment of inertia, being equal to AYC squared plus IXC, which of course we could represent this way as well. All right. Now I'm writing all this. We're doing a little bit of derivation here, but ultimately this is to help you just to understand where some of these equations come from. When you're working through the problems in a fluids problem, you'll basically use, let me just go ahead and then I'll come back in case anybody needs to finish writing this out. You'll basically go to a table like this or a figure like this that will have all of the equations you need, okay? I'll go back so you can finish writing this out. But ultimately, it's that set of equations, and in this case, this is figure 2.18 that I'll show on the next slide. Just give everybody another second or two to finish writing this out. Okay, so it'll look like this. And actually, if you go to figure 2.18, I think there are 2 or 3 more shapes involved. But this is a really handy reference. So you'll want to keep track of figure 2.8 to have these equations handy, okay? Now, we will come back to this. We're going to depart for a moment to talk a little bit about sort of the distribution of force and pressure and where force acts in these underwater surfaces or submerged surfaces that are sloped. And then we'll come back to putting this into action, all right? Okay. So the first thing, we're going to walk through this sort of gingerly. And the reason is that we remember we have 2 very simple questions to ask. The first one is, oh, actually, I think I have this already in here. How big is F sub r? What is this force that is acting on this, this plane right here? And where does it act? All right, a couple of things. It is not uncommon to have, let's say, as this is representing, a sloped wall with some sort of an opening in it. All right. So in this case, we might call this a gate. And this is like some sort of, retention wall. In other words, it is fixed. But you'll also notice that, of course, we would expect to have some sort of angle here that we could work with so that we could figure out from trigonometry how to deal with this this gate and its depth, right? One of the things to also note is that there is a depth here, some h, I don't know, 1, and a depth here, h2, right? And so those 2 depths sort of bound in the way this geometry is laid out the edges of, or the extremes of pressure that are acting on this particular gate, all right? So that's kind of important in the sense that we are trying to calculate how much force is required to open that gate, how much force is required to keep it closed, whatever. We have to deal with the hydrostatic pressure variation, which remains linear with depth, right? Here is pressure on the left-hand side, and it starts at 0. Remember, in a gauge context, it starts at 0, and it increases linearly as a proportional to gamma, all right, for whatever fluid we have. Okay, so let's talk about how we figure out how big FR is and how to figure out where it acts. All right, before we do that, real quick, we do have a clicker question. All right, so let me pull this up. Okay, so go ahead and get your refap going, your iClicker going. I'll read the question and then I'll open it for 60 seconds. So we'll take these sloping glasses. If we isolate a single glass here at the front, this is, by the way, an advertisement, but I saw these and I thought, oh, this is kind of a fun one to think about. If we take these sloping glasses and we isolate a single glass, now I'm gonna draw two things that we might care, 2 points that we care about. If we isolate a single glass, how do the pressures at point 1 and point 2, as they're defined there, compare with respect to the milk that is presumably milk in this glass? A, 1 is equal to 2, B, 1 is greater than 2, or C, the pressure at 2 is greater than the pressure at 1. So let's go ahead and start that. Take your responses, A through C. Let's see if we can get some consensus here. You'll see I kind of picked the fall line of the the slope that the skier is supposedly going down. All right, about halfway through, 90 responses. That's great. We'll go another 20 seconds here. Pause for a sip of coffee. All right. 7 seconds. 5. Okay, there we go. There's our 1 minute. All right, let's take a look at the results. All right. 17 of you said that pressure at 1 is equal to the pressure at 2. 67 of you said pressure 1 is greater than pressure 2. And 11 of you said that the pressure at 2 is greater than the pressure at 1. So the correct answer here is B. Indeed, the pressure at 1 is greater than 2. Now, what may have thrown you off here a little bit is the fact that this is a sloped cup, right? But the point still remains, even if it was a vertical cup, because point 1, if this is horizontal up here, right, the level of the top of our milk, then this depth, I guess I should draw it more vertical, but this depth to get down to here is deeper or greater than this depth to get to here. Therefore, the pressure at 1 will have to be greater than the pressure at 2. There is more milk above point 1 than there is above point 2. Okay, a little bit, I was actually going to draw this the opposite way to go across the other way, but regardless of how you draw it on a sloping glass like this, that bit of physics will and fundamentally gravity will still remain. Okay, great. We have another poll question, but it's not toward the end of the slides. Okay, so let's take. Oh, let me close this guy up. There we go. Out of the way. All right. Okay, so here's that situation again. Note, so we've indicated here. You can see our triangle is indicating the top of our free surface. We draw those little lines underneath to make it look like a reflection. We have some theta slope right there that is the angle between horizontal, meaning this free surface, and the angle, or the pitch, so to speak, of this wall. And we see that H is increasing in the downward direction. So H now is like depth. Okay, it is a depth below the free surface. But the other thing I want to point out is that we also have this Y over here. Okay, Y is an axis of increasing length that is now going parallel to, I should say, parallel to the slope of this this wall. All right. So the first thing we recall that you guys have had drilled into you after this last homework, H is equal to Y times the sine of theta in this case. All right. So wherever we want to go with respect to Y, we can relate Y and H via the sine of theta here. Okay. So first of all, the centroid of our gate is some length y sub c, but rather than going from the free surface, now I'm going to go along this length that is parallel to the wall. So in other words, starting at this point where the water free surface meets the wall, how far do I go down to get to the center of the centroid of this particular shape? And it could be square, could be triangular, could be round. Then we also have another place, another length, y sub r, which is also some length, again, using this intersection of the wall and the free surface as a starting point. How far do I have to go down to get to the location where F sub r is acting, our resultant force is acting, okay? Now I'm going to give this away a little bit, but I will say that in general, y sub r is greater than y sub c. I suppose, yeah, I think that's just about always true. And the reason is that it's because that pressure distribution with depth increases. But let's prove this to ourselves. Okay. Related to each one of these, there are depths that are sort of akin to this, right? So we have h sub r. Oops, my h sub c did not reveal itself. There it is. Okay. So now, along with going this length along the wall, we also have some depth of water that is related to the centroid, and we have a depth of water h sub r that is related to the location where F sub r is acting on our gate as well. So a couple of more equations here. H sub c is going to be equal to y sub c times the sine of theta, right? If we follow our general equation. And we can also say h sub r is equal to y sub r times the sine of theta. So if we can get one of these, we can know the other, right? So for example, if we know that the elevation of water should always be constant for some reason, or it's measured in some way, and we know then we can easily either measure or calculate h sub c and h sub r, it's not difficult to also translate that to y sub c or y sub r, if we already have those, okay? So h sub c is a vertical distance. That should be an L. Distance from the fluid surface. We're getting some noise from someone. Maybe it's Elizabeth? Not sure. That's the one that's green. Thanks. From the fluid surface to the centroid of the gate. Actually, to be more precise, the centroid of the area of the gate. Okay, and this is not the first, well, it's maybe the first. This will not be the last, I should say. Problem where you'll see basically the wall sort of hatched in this way, and then the gate is shown as a different color. And the gate could have a hinge at the top. It could have a hinge, a shaft in the middle. It could have a hinge down at the bottom. And we'll talk about a couple of those different cases and what they mean. H sub r is a vertical distance from the fluid surface. Oops.
64.12
to the location where F sub r acts, and then y sub c, of course, is what we call the center of pressure. Oh, I went in lowercase. Hopefully you guys can still read it. The center of pressure, okay? So we need to figure out how to calculate h sub c, h sub r, F sub r, how they all relate to each other, and y sub c and y sub r, okay? And we're going to, as you can imagine, the y sub c and y sub r, I guess mostly the y sub r actually, will rely on the moment of these shapes and relative to the axis as we've drawn it sort of normal back here, right? You can kind of see this axis back here, normal to our plane. Y sub r and y sub c will start to use these centroid and moment analyses that we talked about a few slides ago. Okay, let's focus in on the gate itself and figuring out HR, or pardon me, FR, the resultant force from the pressure. So if we zoom in on this, if we have at any, we could think about measuring pressure or expressing the pressure acting from the top of this to the bottom of this in PSI, right? And so maybe one way of thinking about DF is that DF is some amount of force that is acting over like a square inch, right? So a square inch times the pressure at that depth will give us the force acting there. Okay, so we can think about this differential force being equal to the pressure at that depth times the differential area over which that force is occurring. Okay, so again, another way to write this is gamma times H times dA, right? Now, it turns out, recall that we can also write H is equal to y times the sine of theta, given that we have our gate on a slope here, all right? So I could replace in this dF equation H and say that dF is equal to gamma times y sine theta dA. Okay? So we can now represent this force anywhere on the area as a function of depth, h, or as a function of length along the wall, y. And we do that with sine theta. Okay, so FR, our resultant force then, is equal to the integral over the area of all of the dFs that we have, right? And so we can rewrite this then as the integral over the area of gamma y times the sine of theta dA, which is also equal to gamma times the sine of theta. Those two are constants that we can pull out, times the integral of y dA over the entire area. And remember that this is, that's supposed to be a bracket, but anyway, this can be just this integral can be represented as y sub c times a. So we can now rewrite this as the resultant force is equal to gamma times y sub c times the sine of theta times our area, whatever the area of our gate is. And we can also write, because this value is the same as h sub c, we could also write it in terms of depth. So this version is written in terms of y, the length along the wall. We can also write this as F sub r is our resultant force is equal to gamma times h sub c times a. Sorry, that should be a c. So the centroid depth, what is the centroid depth? Okay, now the reason this works is because the centroid of our shape should have the same length above it as it does below it in it, whatever that dimension is along the y direction. And therefore, the pressure that's acting there, acting across that face, is it's increasing, but it's evenly distributed above and below the H sub C, right? So the centroid. And therefore, we can move forward with this approach, and it works pretty well for basically taking care of the changing pressure with depth, because we basically taken an average from the two extremes. The shallowest and the deepest are averaged right at the centroid. Okay, and so we can do this in terms of depth, or we can do it in terms of length along the wall. Now, let me just rewrite this for us. The resultant force is equal to gamma times the depth of the centroid times A. We can write this a little bit differently as well. Remember that pressure is equal to gamma times depth. So the other thing that we can do is say that this is equal to some pressure that is measured at the centroid, right? At the centroid, again, the centroid is of the shape of our gate. So this could be rewritten as just the pressure at that centroid depth times the area. Again, that averages out, working with the centroid averages out the lowest and highest pressures that occur as depth changes to get this FR value, okay? So when we work on these plane surfaces, the magnitude of the resultant force is based on the pressure at the centroid. The direction of FR is going to be normal to the plane, right? And FR will not pass through the centroid. So this is really the most important point. We can use that sort of average pressure over the area or depth range of our gate to figure out FR, but it does not act at the centroid. So this is where these problems get a little bit confusing. The centroid is important to us to figure out the magnitude of the resultant force, but its location of action really occurs generally below that, but not at the centroid. Okay. All right. So let's talk about how we figure out where this occurs. So where does FR occur? So the location of FR, as it turns out, has to match the moment of the distributed pressures. And we have this distribution that is linearly increasing with depth in the H direction, but that's occurring along this sort of Y line of interest, right? So let's just we've got indicated up here at the top, we actually mean the moments here, okay? So let's take some moments about B. So the moment of pressure forces, and we could do this with a bunch of DFs, right? A DF that is up high versus a DF that's lower, and both of those are going to have different pressures acting on them. So let's do this analysis. So we do a moment about point B. Oh, ABOUT, yep. Which is at the top of this. So B is basically a point at this intersection of where the free surface behind the wall meets the wall, and then that becomes the 0 point for this axis that allows us to move in the Y direction. Okay, so the moment about B due to DF. Well, actually, no. Actually, let's do this with respect to F sub R, rather than working on a bunch of DFs. Is basically represented as the moment of this force FR will be equal to the magnitude of that force, right, multiplied by the length from B to F sub R. And so in this case, that is Y sub R, right? So that's that moment, right? So So we would go down this wall from B to where FR acts. That is some depth Y sub R. And if we take the moment about B due to DF, then we would get MDF, the moment invoked by DF, is equal to the integral of the area of Y dF. Okay? Okay, well, we've got a little more work to do. The next two slides that I have are blank for us to just have some room to work. And if needed, I'll jump back to this slide to get us started. I guess one thing I forgot to do was copy this image to the next two slides, so we may jump back if we need to just kind of look at how things are distributed. But for now, remember that there's going to be some general Y that gets us to DF, but F sub R, that resultant force, has a very particular location of action, and it is a distance Y sub R from this intersection point. So along the length of the wall, from where the fluid on the left-hand side meets the wall. Okay. All right. So next slide here. The moment for our resultant force, we said, was equal to F sub R Y sub R, right? And this can be rewritten then as gamma YC. So that is just the force value. Oops, I forgot my sine theta. So that's now written in terms of moving down the wall at its angle. And then when we multiply by A, we get the full force. So this first part was the pressure. When we multiply it by the area of our gate, we get the full FR. And then, that was a capital R, sorry. And then we multiply by Y sub R, right? So we've just re-represented that resultant force as what we had done a couple of slides ago. When we look at the moment for DF, we said that was equal to the integral over the area of our gate of Y dF, okay? Now, from before, just as a reminder, that's a terrible E, but it's an E nonetheless. All right, DF is equal to gamma Y times the sine of theta dA, right? So that's sort of our differential force acting over a differential area on the gate. And this gives the following. MDF then is equal to the integral over the area of gamma times the sine of theta times y squared dA, which is equal to gamma times the sine of theta. So we pull those constants out of the integral, and now we have the integral of over the area of y squared dA, and this should now look a little bit familiar from what we said with our moment analysis. This is Ix, moment of inertia, and this is now equal to, we can re-represent it as gamma times the sine of theta now times Ix, our moment of inertia, okay? So the equation, so we would get to this point, and we'll go a little bit further on the next slide, but you can see where the moment calculations formulas now come in. If this was a rectangle, if this was a triangle, if it was a circle, those all have different IX representations, right? And so that's why you want to keep that table, I think it was figure 218, handy, because you'll want to be able to reference the shape, the dimensions. Sometimes they have like an X and a Y. What is the height? What is the width? Those dimensions and how they're represented in those shapes will be important as well. All right, let's go to the next slide. So now, if we're setting the moment about our resultant, or for our resultant force, equal to MDF, will give us the following. Gamma y sub c times the sine of theta times a y sub r. Okay, so that was our moment for the, let me just make sure. Yeah, that's our moment for the resultant force. We put that equal to now MDF on the right-hand side, gamma times the sine of theta IX. And we would note that essentially we can cancel out the gammas and so forth, the sine thetas, and what we end up with is y sub r, the location of the resultant force, is equal to Ix over y sub c, the distance to the centroid, times area A of our gate. Okay? So now, we're going to combine y sub r is equal to this moment of inertia over the distance to the centroid times the area, with the parallel. Oh, those are supposed to be L's. I'm too fast with my L's. Parallel axis theorem. And you may recall, basically, it will say that Ix is equal to Ix of the centroid, Ixc, plus the area times the distance to the centroid squared. Basically, we would get y sub r, the location, the distance to the resultant force along the wall, is equal to y sub c plus Ixc over y sub c times A. Okay, so that is the general equation that we need for all surfaces that are submerged and are not horizontal, to let us work beyond the location of the centroid. Okay, so Ixc, so this will work for squares, it works for rectangles, it works for circles, whatever the shape is, this is what works. The key is knowing how to calculate the area of that shape and what is this moment of inertia with respect to the centroid. Okay? So when I said earlier, Fr, the resultant force of this pressure distributed across the gate, is always greater than y sub c, this is why. Okay? You have y sub c, and then you add this fraction that is a little bit more to get past it, to get to the point where Fr acts, right? So that looks like this. So Fr always acts below the centroid. This is the equation we wrote on the previous slide. And this is the difference here. So here's y sub c coming down to this point. The difference between y sub c and y sub r is ixc over y sub c times a. Okay? So it's important then that we are working, we are thinking carefully about what happens in the h direction and what happens in the y direction. And again, we can relate those two to each other, but you can see how on these planes or surfaces that are at an angle, so they're not horizontal and they're not vertical, we have to work with these y's and these moments of inertia. Now, if this were to be a vertical wall and we had a gate somewhere in it, part of what makes that easier is that you're not translating between h and y, right? Those are the exact same values then. That is, the depth to get to the centroid of our gate is the same as the y on the outside to get to the centroid of the gate. So we would use the same equations, perhaps. We could use the same approach, but it would just make things a lot easier because we're not, perhaps, in a problem you could imagine that you're given a bunch of depths, a bunch of h's, and you've got to somehow figure out the y's to go with them. All right? Okay. Let me just write this. Y sub r should always be greater than y sub c. Okay, so let's do a quick little reality check here. One more clicker question. Nope, that didn't come through. All right, we've got these 4 locations. The Georgia Aquarium in Atlanta, if you've never been there, it's super cool. I think it's kind of expensive to get in. I want to say it's like $70, but this is totally worth the experience. You walk through a tube, glass all the way around you. I can't remember how thick it is. I want to say it's 4 inches, but in any event, it doesn't look like there's a lot of parallax, and you just get to be a person submerged looking at all of these fish moving around you, in particular whale sharks and so forth. So at the Georgia Aquarium in Atlanta, you have this semicircular observation tube at which 4 points are identified. I've drawn them into this figure. The pressure on the outside of the tube is greatest at which of these points, A, B, C, or D. So let me go ahead and get this guy going and go ahead. We'll take a minute for you guys to respond to that. A, B, C, or D, which one of those is the highest pressure on the outside? So in the fluid that's being exerted from the fluid above the tube. Oh no. Oh no, I did it. Okay. Okay, I got 89 responses. Go 10 more seconds here. 90. 4, 3, 2, 1. Okay, so let's go ahead and stop and take a look at the responses. So 62 of you said A, a couple of you said B, a few said C, and 22 of you said D. So on the outside of this tube, we are going to assume that if we're surrounded by seawater, that somewhere there's a surface up there that is flat, right? Mm-hmm. So the highest pressure that's acting on the outside of this tube is indeed at A. So most of you got that right. We can go with the majority on this one, and that works out. And it's only because that is the deepest point. So regardless of whether we have a curved surface or a flat but sloping surface, remember that hydrostatics is still about the depth of immersion, the depth of or the height of water or whatever a fluid is above a particular point. All right? Good deal. Okay, so let me go ahead and close that for today. All right, the next thing that I had queued up here was to work through a problem. Okay, it's this way. As an example, all right. So we've got about 13 minutes left in class. I wanted to draw out this problem and talk about how we work through it. All right. So the question is, I don't have a good figure for this, so I'm going to draw it on the right-hand side after I read through it. A circular 2-meter diameter gate is located on a sloping side of a swimming pool. The side of the pool is oriented 60 degrees relative to the horizontal bottom, and the center of the gate is located 3 meters below the water surface. When we say located below the water surface, that's an H, okay? So we'll draw that in a second. Determine the magnitude of the force, well, the water force acting on the gate and the point through which it acts. So very simply, what is the magnitude of FR and essentially what is YR, the location at which it acts. Now, it does say the magnitude of the water force acting on the gate and the point through which it acts. That's a little bit nebulous in that it's either YR or it's HR, right? One of those two. But again, we can translate between the two using the sine of theta. Okay, so real quick, let's draw this up. You've got a question like this. We've got this wall coming down. It's sloping. We then have our gate. I'm going to just kind of blow up this gate just so it looks different. It doesn't mean it's supposed to be necessarily thicker than the wall. And then there was a note that from the bottom of the, oops, that's supposed to be curved, that this angle is 60 degrees, okay? We were also given that the center point of this gate has a depth of 3 meters. So H sub C, is that right, to the centroid? And the center of the gate, H sub C, is equal to 3 meters. Okay. All right. What else? We also said that this was 2 meters tall, or 2 meters in height, and I suppose that, you know, the other two things that I could draw in, one is from here, you know, what is y sub c? That would come to here. So I'm just going to kind of draw this out a little bit. So this is some, oops, that's terrible, but a y sub c. And then somewhere below this, we expect FR. And one thing I guess I didn't say, but I hope everybody recognized already, is that FR should be acting normal to the gate, right? It has to be at a right angle to the gate. Okay, so y sub c will be that length, and then there's some y sub r that comes down to this length. Okay? All right, so how do we go about solving this? The first thing we're going to want to do is calculate FR, and then we'll calculate where it acts. All right, so for now, let's start with calculating FR given the equations that we talked about a few slides ago. So I'll do that on the next slide here. So the resultant force could be written as the pressure that's acting at the center of our gate area times the area of that gate, right? And we said it was 2 meters and it was circular. Isn't that right? Yeah, 2 meter diameter. So sorry, when I was talking about height or 2 meter dimension on the previous slide, 2 meter diameter means it's 2 meters wide and 2 meters tall. All right. So we can rewrite that pressure as gamma of, in this case, water, times this H sub C, the depth to the centroid, times the area of our gate. Okay. So we were given H sub C, that's equal to 3 meters. And we can take gamma water to be 9.81 kilonewtons per meter cubed. Now, in part, I can write that because I've kind of memorized it, but it's essentially, remember that gamma, the specific weight, is equal to the density times gravity. And in this case, when we use the density of 1,000 kilograms per cubic meter for water at 4 degrees C, multiply that by 9.81, you get 9,810 newtons per cubic meter, and I'm just going to leave it in kilonewtons for now for the second. Okay, then we can work out the area, which is going to be the area of a circle. Recall pi d squared over 4 or pi r squared. So FR is equal to 9.8 kilonewtons per meter cubed times 3 meters depth times the area, which is going to be pi over 4. And then our diameter, we said, is 2 meters squared. And when we work that out, we should get 94.2 kilonewtons. Okay? Now, real quick, dimensional analysis says if I'm going to get an area and I multiply it by a length, I should have length cubed, right? So meters cubed will cancel with meters cubed in the denominator. So I should just end up with a force. So that part was pretty easy. We just figured out F sub R. That's pretty straightforward. Now we've got to figure out what is Y sub R. Oh, that was supposed to be a question mark. Okay, equals what? All right, so we can recall that we can write I just want to make sure I'm consistent with the way I did it before, because I think I just took a step. Yes, okay. So Y sub R is equal to recall we said the length to the centroid plus IXC, the moment of inertia, respect to the centroid over Y sub C, the distance to the centroid, times A, the area. And then what you would figure out, I didn't bring it up to look at, but IXC for a circular shape looks like this. We would end up with IXC is equal to pi r to the 4th over 4. So r here is radius, right? I could have, it was given in radius, so I just kept it in that. But in this case, we know that if the diameter is 2, our radius is equal to 1 meter, okay? So when we work this out, we basically get pi over 4 meters squared, right? That we can do that math here. I'm going to leave that alone for just a second. And in this case, let me go back to my drawing. One thing I want to point out is that we had been previously noting that I think we had noted that this was our angle that we cared about before. And it turns out that because the ground, I haven't drawn it as straight as I could have, as horizontal as I could have, but the ground and the water surface should both be horizontal, right? So they're parallel to each other. And this this single wall that, kind of comes in between them at an angle, or that's not perfectly vertical, means that we should have 60 degrees on both sides. Okay, both of those, we were given this one, but from geometry, basic geometry, we can say that is also 60 degrees. So we don't have to necessarily take this a step further and start to think about cosines instead. So we can say that it was H is equal to, my solution's a little bit different here. H. So H sub C is equal to Y sub C times the sine of 60 degrees in this case. And so we could solve for Y sub C is equal to 3 meters divided by the sine of 60 degrees comes out to be 3.46 meters. Okay, so what I'm trying to do here ultimately is get us enough information to make this work out. Now, I needed y sub c here and here so that I could calculate y sub r, and of course the IXC occurred here, and we can calculate the area again. So now we should have enough information to say that y sub r is equal to 3.46 meters plus pi over 4 meters to the fourth. Oh, sorry. I'm not sure if somebody caught this in the chat. Sorry about that. This should be pi over 4 meters to the fourth. And I still can't write it. Fourth. Let's just get rid of it. Meters to the fourth. Ugh, goodness sakes. I could say it, but not apparently do it. Okay, so we have 3.46 plus pi m to the fourth, and then we divide by y sub c, which is 3.46 meters, and our area is pi over 4 times 2 meters, our diameter squared. This should be squared. And when we work this out, we end up with y sub r being, this is calculated as a difference, so it is 3.46, so 3.53 meters. Okay, so real quick, we're just about at time, but we basically figured out y sub c from h is equal to y sub c times r, times the sine of theta. We figured out y sub r from the complicated stuff that included the moment of inertia for a circle. We knew h sub c, and we figured out f sub r in a pretty straightforward manner as well. Okay. With that, I will hang out and take any questions if anybody has them. Just remember, homework 4 is now